All right, so basically, anytime something burns, it's a chemical reaction. So when a substance undergoes a chemical change, a chemical reaction takes place. So what is the law of conservation of mass? And basically, the law of the conservation of mass states that mass cannot be created nor destroyed. So all the matter in the universe that ever was will ever be. Okay? There's a lot of truth to that, especially within the lifespan of a human being. So then it says chemical equations are useful way to balance the equations. The description of a chemical reaction tells you the substances present and before and after the reaction. So basically, to summarize what we're going to talk about is if I have a certain amount of oxygen and a certain amount of carbon and I do some chemical reaction with the two, I still have the same amount of carbon and the same amount of oxygen because the elements are just elements. And I can combine elements to form molecules, but I'm going to have the same amount of stuff. So what goes in comes out, basically. So substances that undergo a change are called reactants, and the new substances formed as a result are called products. So those are terms that are kind of important. So then using equations to represent reactions, during a chemical reaction, the reactants change into products. You could summarize this process with a word equation. In other words, you have these reactants right here, okay? And those reactants these reactants become products. So it says to describe the burning of a charcoal, you can write reactants and products in of the reaction in the following word equation. So if I have carbon and I add oxygen to it, in other words, that first slide was like a carbon, mostly carbon, right? Charcoal is mostly carbon. And when you burn it, it actually combines with the oxygen and then it releases carbon dioxide. That's a byproduct or product of it. So then write the reactants and products as a chemical equation. So basically the carbon burns with oxygen. Oxygen in its natural state is what we call a diatomic molecule. In other words, oxygen travels in pairs. They're on the buddy system. And then when you burn carbon, in other words, that chemical reaction we saw at the beginning, charcoal burning, it releases the gas carbon dioxide. Notice that I have one carbon here per 2 oxygen, and I end up with the same thing over here. So a chemical reaction is a representation of the a chemical equation is a representation of the chemical reaction in which the reactants and the products are released as formulas or are expressed as formulas. You can read the equation carbon plus O2 is equal to carbon dioxide as carbon and oxygen react and form carbon dioxide, or the reaction of carbon and oxygen yields carbon dioxide. So during these chemical reactions, the mass of the products is always equal to the mass of the reactants. This principle is the law of conservation of mass. So we could actually measure how much carbon we start off with based on the mass and measure how much oxygen we start off with based on the mass, and if we add it all up, that'll be how much carbon dioxide we have, okay? So when charcoal burns, the mass of the carbon dioxide produced is equal to the mass of the charcoal and the oxygen. So whether you burn 1 carbon atom or 6 carbon atoms, the equation used to describe it is the same. The ratio, remember we learned this a couple chapters ago, the ratio remains the same. So the carbon will burn with 2 oxygen and create carbon dioxide. So if I have 2 carbon atoms, they're going to combine with 4 oxygen atoms to create 2 molecules of carbon dioxide. But notice I have 1, 2, 3, 4, 5, 6 carbons 1, 2, 3, 4, 5, 6 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygen molecules. And then after the reactants react, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygen atoms. So what I start off with is what I end up with. So why must chemical equations be balanced? Well, because of this conservation of mass. In order to show that the mass is conserved during a reaction, a chemical equation must be balanced. Now, sometimes not every carbon will interact with an oxygen. If you have more oxygen than you have carbon, and there'll be stuff left over. And sometimes when you have 3 and 4 elements that are combined, they don't all interact with each other. In other words, you might have 5 elements in a chemical reaction that forms 2 products. We'll talk about that later. You can balance the chemical equation by changing the coefficients, the numbers that appear before the formulas. You can change the coefficient, or when you change the coefficient, you change the amount of the reactant or product represented in the chemical equation. Water is a compound made up of elements of hydrogen and oxygen. You can balance the chemical equation by changing the coefficients, the numbers that appear before. You can also, when you change the coefficient, you can change the amount of reactant. Those are the two? Huh. They got the same slide in here twice. So anyways, if I have hydrogen, which is H2, and then I have O2, notice that over here I have 2 hydrogen. Over here I have 2 oxygen, but over here I have 1 hydrogen and 2 oxygen. So there's got to be some sort of ratio because I got to have the same amount that I start off with. So the truth is I'm going to have 2 H2s, right? I'm going to have 1, 2, 3, 4 hydrogen atoms and 2 oxygen atoms. So that leaves me with 1, 2, 3, 4 hydrogen atoms and 2 oxygen atoms. How did I make that happen? I put this coefficient of 2 in front of the reactant of hydrogen. Hydrogen is also a diatomic molecule. Okay? They like to travel in pairs. Okay? So basically, when we balance an equation, we want to make sure that, by the way, what's 2 times 2? 4. So that's what I'm doing. If I say 2 times 2, that means I have 4 hydrogen. Okay? But what's 2 times O? Right? So you got to think of this as like H2O being in parentheses. I have 2 molecules of H2O. That tells me how many things I have. Okay? The chemical equation for the formation of water is now balanced. Each side of the balanced equation has 4 hydrogen atoms and 2 oxygen atoms. According to the balanced equation, 2 molecules of hydrogen react with 1 molecule of oxygen to yield 2 molecules of water. So balancing chemical equations, the process for that is basically you write the balanced equation for the reaction between the copper and oxygen to produce copper oxide, or CuO, right? So we're going to write down the reactants. Copper is just copper, Cu. Oxygen is diatomic, so it's going to be O2. And we want to have 1 copper to 1 oxygen. Well, I start off with 2 oxygen, but I need a 1-to-1 ratio. What do you guys think we're going to need to put the coefficient at? I'm going to need to make, I want 1-to-1, so I'm probably going to need 2 coppers to 2 oxygens. Let's see. So what we want to do is write the chemical equation with the reactants on the left-hand side and the product on the right. Then we'll notice that over here I have 1 copper but 2 oxygen. Over here I have 1 copper and 1 oxygen. So what if I do this? Well, now I have 2 copper and 2 oxygen, but over here, how many copper do I have? Just 1, so it's not quite balanced yet. So I could change the coefficient of copper in order to balance all the copper atoms. So now I have 2 copper, 2 oxygen. The 2 in the front is saying that I have 2 copper atoms. When I say O2, I'm really saying 2 oxygen atoms. But now this 2, the coefficient of this molecule means that I have 2 copper and I have 2 oxygen. So now it's balanced. The number of atoms on the left equals the number of atoms on the right. That's the conservation of matter. Let's do another example. Hydrogen chloride, or HCl, is an important industrial chemical. Write a balanced equation for the production of hydrogen chloride. Well, remember this is diatomic and this is diatomic. So that means I'm always going to have 2 hydrogen going into this, and I'm always going to have 2 chlorine atoms going into this. While on the right-hand side, I need to make sure that I have 2 hydrogen. Because I have the coefficient of 2, that's saying I have 2 molecules of hydrogen chloride, which means I have 2 hydrogen atoms and 2 chlorine atoms, which is what I have on the left-hand side. So the matter is conserved. So now balancing the following chemical equations, and we're going to do a worksheet on this. Right now I'm just talking about the concept. We'll actually do a bunch of work on this. Let's do the first one. I have 2 hydrogen and 2 oxygen. I need to make sure that I have 2 and 2. So over here I have 2 hydrogen, that's good. But I have 1 oxygen and 2 oxygen. If I put a 2 in front of the hydrogen, that gives me 2 times 2, which is 4 hydrogen. And then the 2 in front here gives me 2 times 2, so that gives me 4 oxygen. Now if I put a 2 here in front of this, that means I get 2 times 2 hydrogen, which is 4. Then 2 times the oxygen, that gives me 2 oxygen here and 2 oxygen here. That's 4 oxygen. So I've got 4 and 4. Similarly, we basically do the same thing for part B. I'm going to kind of skip past these because we're going to do those in class. Why do chemists use a mole? So this is the last thing I want to talk to you guys about. Because chemical reactions, and then tomorrow we're going to just do a whole worksheet of balancing equations. It might take 2 days, to be honest with you. Because chemical reactions often involve large numbers of small particles, chemists use a counting unit called a mole to measure the amounts of a substance. So a mole is an amount of a substance that contains approximately 6.02, yes? Huh? Yeah, the next school day. No, you guys come to school on Saturday. I'll be here. We could sleep in though. Come in, don't come. Let's meet here about 10:30, okay? No, of course I mean Monday. Anyways, a mole is the amount of substance. Now, it's about 6.02 times 10 to the 23 particles. So that's basically 6 followed by 23 zeros. That's a really big number. While when you think about the size of an atom or a molecule, it's very small. So a mole of iron is this many particles, okay? This is known as Avogadro's number. We use that a lot in chemistry. The atomic masses are based on Avogadro's number. We'll just leave it at that for now. So then you might count a pair of shoes, eggs by the dozen, paper by the ream, which is 500 sheets. So to count particles of a substance, chemists use a mole. It's just a convenient way. I don't want to overwhelm you. This is supposed to be 10 to the 23rd particles, but some reason when I switched it to Google Classroom, it didn't do the superscript. So then counting with moles. So the mass of 1 mole of a substance is called the molar mass. For an element, the molar mass is the same as the atomic mass expressed in grams. So where this number comes from is if I have this 6.02 times 10 to the 23rd particles, that should weigh the atomic mass in grams. Okay? So carbon has an atomic mass of 12. Why? Because it has 6 protons and 6 neutrons, which makes up the majority of the mass of carbon. If I take a mole of carbon, right, 6 followed by 23 zeros, it should weigh approximately 12 grams. Okay? So this is important because we're going to use 2 units, as you'll see on today's reading guide assignment. There's the atomic mass unit, and then there's grams. Grams is a mass based on molar mass, right? 1 mole of that substance. The molar mass for sulfur is 32.1. It's the same number, just different units, okay? You can calculate the molar mass of a compound by adding up the atomic masses of its compounds or component atoms and then expressing them as this sum in grams. So carbon dioxide, the molecule is composed of 1 carbon atom, which has an atomic mass unit of 12, plus 2 oxygen. Pay attention, this is on that reading guide today. 2 oxygen atoms, which is 2 times the atomic mass unit of 16, or 32. If I add all that together, 32 plus 12 is going to be 44. So carbon dioxide, 1 carbon, 2 oxygen, has a molar mass of 44 grams. I'm going to let you know right now, there's a question on today's assignment where they ask you, what is the molar mass of carbon dioxide? And there are 2 choices. It'll say 44 atomic mass units or 44 grams. If it says molar mass, then your units has to be grams. Okay? So then molar mass conversions, and we're going to do a whole worksheet on this too. Once you know the molar mass of a substance, you can convert moles of the substance into the mass, or the mass of the substance into moles. The molar mass of carbon dioxide is 44 grams, which means that 1 mole of carbon dioxide has a mass of 44 grams. This yields the following conversion factors. Now, this is important for chemical reactions, so I'm going to just front load a little bit. If Mr. Adams wants to, let's say Mr. Adams is doing research in chemical engineering and I want to synthesize or create a chemical, and I know the elements that go into the chemical, I can carefully make calculations as to how much of one thing I need to combine with the other. And I want a very pure product, so I would weigh out how much carbon I would use, and I could weigh out how much oxygen would be necessary to create carbon dioxide. Does that make sense? By doing these conversions, okay? Anyways, we'll do a lab on that. So suppose you have 55 grams of carbon dioxide and you want to calculate how many moles of carbon dioxide you have. Well, just like any other unit conversion, if I have grams here, I want grams on the bottom so I can cancel my grams with grams. That leaves me with moles on the top. Now, the relationship is that 1 mole of carbon dioxide weighs, or has a mass of, I shouldn't say weighs, has a mass of 44 grams. Then I just plug this through, multiply 55 times 1, divide by 44, and I get 1.2 moles of carbon dioxide. So 55 grams of carbon dioxide contains 1.25 times 6.02 times 10 to the 23rd. You can double check your answer. Again, if I put moles on the bottom, or if I start with moles here, I want to put moles on the bottom here because then this moles will cancel with this one and it'll leave me an answer in grams. If I say 1.25 times 44 divided by 1, I get 55 grams. So how can you calculate the mass of a reactant or product in a chemical reaction? In chemical reactions, the mass of the reactant or product can be calculated by using a balanced equation and molar masses of the reactants and products. So a cake recipe tells you how much of each ingredient that you use. Chemical equations are kind of like recipes when it comes to making new substances. So one of the summers or years that I was at Notre Dame, we worked with ionic liquids. Now, ionic liquids, basically you take ions that had a positive or a negative charge, and when you combine them, they formed a salt, and that salt was a liquid at room temperature. Well, there's a whole list of cations and anions, and you just need to know how much of one you need to mix with the other. So they literally just kept mixing stuff together. So they would do these calculations, weigh out how much of the cation they needed, weigh out how much of the anion they needed, and put them together. Now, I'm really oversimplifying it. There was more than just, they used molecular ions too, which is a little more complicated, but basically they just kept making this stuff, and they used exactly what I'm going to be teaching you over the next couple days. So then in a balanced equation, the number of atoms for each element on the left equals the number of atoms on the right. So when I say the formation of water, I've got two molecules of hydrogen 2, right? Plus 1 molecule of oxygen 2, or O2. That should equal 2 molecules of water, H2O. Well, if I want to find the molar mass of that, I know that the molar mass for hydrogen is 2 grams. The molar mass, well, it's actually 1 times 2. Does that make sense? And then oxygen has an atomic mass unit of 16, but I have 2 of them, so 16 times 2 is 32. And then I have 2 moles of 18 grams. So if I crank through the math to calculate how much oxygen is required to make 144 grams of water, we start with this balanced equation, and then I determine that I want 144 grams of water. Well, the ratio, 1 mole of water weighs 18 grams. So, I forgot to do this. So when I add all this up, 2 times 2 is 4, 1 times 32 is 32, and then 2 times 18 is 36, all right? 4 plus 32 is 36, so everything adds up. This is the molar mass, okay? So 2 molecules of water has a molar mass of 36. So then you work backwards. What would 1 molecule of water have? A molar mass of 18, which makes sense, right? So then I'm going to come in here and I'm going to say that 1 mole of H2O is equal to 18 grams, or has a mass of, this is the conversion ratio, 18 grams of H2O. I put the grams on the bottom because I want to cancel with these grams, do the math, and I get 8 moles. So that's helpful, but the question says how much oxygen is required? Well, to figure out that, we write the conversion factors of 1 mole of oxygen and 2 moles of H2O, or 2 moles of H2O and 1 mole of oxygen. So if I have 8 moles of water, I want 2 moles of water on the bottom because I want to cancel this unit with this. In other words, this is the ratio. You have 1 mole of oxygen, or O2, and 2 moles of water. And this goes all the way back to this balanced equation. So then I hit it with this conversion factor. I do the math, and I have 1 mole of oxygen, or O2. So the question says, well, what is that converted into a molar mass? Well, 4 moles, in other words, there's 32 grams of O2 in 1 mole of O2. So we put the moles of O2 on the bottom here, so they cancel here. Do the math, and I need 128 grams of O2. So basically, to produce 144 grams of H2O, you must supply 128 grams of O2. Okay? And that's it for today.